Hey, good morning, everybody. Physics reaction video number 15. This is actually a friend of mine. I was searching around. What did I do? A search for honors physics. I tried looking for honors physics, and this is from several years ago, but I haven't seen this video, so let's go.
Hello, wonderful physics students. Welcome back. In this
Awesome.
video, we're going to go through some simple examples using electric potential and electric potential energy.
Oof,
Okay,
tough. Sign
let's
problems all over the place.
so in this first example, point A is at an electric potential of 750 volts. Point B is at an electric potential of 950 volts. An electron is observed moving at some speed at point A. When it is observed at point B, will the electron speed?
So that little hitch was really interesting because it's funny as she was reading this sentence about what it says. This one here, an electron is an electron is observed moving at some speed at point A. I was thinking, oh wait, oh this would be a cool magnetism problem. I don't know, my brain was just going to magnetism for some reason, and so it was interesting when she sort of paused here. I was also pausing, but I actually wonder if she's pausing because this when observed at point B, could that possibly be a different time, right? Because in a little bit of time, this electron is going to be either gaining or losing some of this potential energy. So maybe it'd be going faster. So I actually wonder if that's what made her pause. My guess is we'll never know. And you know that I'm really, really excited about watching teachers deal with that sort of critical thinking in the moment. And so my guess is she paused for a second and then immediately recalibrated her brain and kept going. So very cool. Let's see. So the question: when observed at point B, the electron speed will have. Oh, and see, I even got it wrong. It is at a different time. It is at a different time. So an electron is moving at some point at point A, and then at point B. Aha! So it really is going to be the gaining or losing some potential energy. Um, and also, I think it's really, really interesting because this observed at point A could be interpreted a couple of different ways. Like point A is some observer and saw far away this electron, which is not what they mean here, or that when it's at point A, someone else observed that it was going at some interesting speed. So, so it's really interesting again to have videos so you can really sort of, as you read the problem out loud, you can emphasize certain words. And so I actually think this is a really interesting problem because there's very likely a potential sign mistake.
Speed have increased, decreased, or remained the same? Da da da. Okay, so this example is wonderful because you don't need to calculate anything. It's
Yes.
all going from concepts. So, as always, the first thing I would suggest that you do is draw a picture. And this picture is pretty simple. You have just point A and you have point B.
Cool.
Now,
I was just thinking about this drawing and how, often we might want to draw the field, for example, but this doesn't actually mention a field. It's just we only know a couple of things. We know that it's 750 volts at A and 950 volts at B. Now, a field is what generates that potential, but we don't actually need it. But so already I'm starting to think of different ways you can do this problem. You say, well, it went from A to B, so its volts went from 750 to 950 and have to turn around to figure out whether that means it should speed up or slow down. But you could also draw the field and talk about any work that gets done. There's lots of fields that can produce a potential of 750 here and 950 here, right? But the beauty of electric potential is that it doesn't matter whether that field is a really squiggly thing or just a straight line. The amount of work it takes to go from A to B is going to be the same. Very cool.
at point A, we have 750 volts, and at point B, we have 950 volts. And our electron
New color.
is
Yes.
a negative charge,
Ooh,
and
being very
this
clear about the
moving
negative charge.
this way. So there's our velocity. Okay. Now, this brings up a good point here. We have V for voltage and V for velocity, and it can get
Ooh.
really confusing. So what I have done is that I tend to like do a cursive V for
Yes.
velocity
Oh, that's so cool.
and a capital V for voltage. Sometimes even just doing this.
When I was in school and college, my handwriting at the time was all uppercase letters. And so I did struggle with this. And I actually really appreciated it when my physics teachers would tell me, okay, well, here's how I'm going to do it. Here's how you can do it. And I've always been struggling a little bit as a teacher when we're going, let's say, working from a book, and the book uses bold and colors and italics, and most people's handwriting doesn't include all of that. So I really like this tiny little tutorial she's given about how to read her handwriting. The other thing that I wanted to say is that I don't think this direction matters. Let me think about that. I mean, it's got to find its way from A to B or possibly B to A. It doesn't actually say that this happens later in time. But because this is an energy problem, direction doesn't matter. Boy, my brain is really trying to figure that out. I mean, obviously, going straight from A to B is an easy way to do this problem. And as I said before, it doesn't really matter because the answer is going to be the same. This, if all we're going for is this increase, decrease, stay the same, it's not going to matter. Very cool.
For voltage, or this. But I try to make my cursive V's. Yeah, cursive. Anyway, back to the problem. All right. So, well, the first thing that we could think about is our change in potential. Did our change in potential go up or down? All right, so we go from 750 to 950. So our change in potential increased. So our change in potential is positive. All right. So then,
very cool.
Well, potential is in that equation with potential energy. So
did you notice that? Did you notice how she looked up and tried to think it through? It felt real to me. Might not have been real, but it felt real, like, okay, just working it out, right? For me, when I'm doing the solutions, I'm like, I want to make sure I get it right. So even if I've done it before, I want to make sure, hang on a second. Let's see, the potential goes up, potential energy, right? So I really, really liked sort of her mannerisms as she was doing that because she's making it clear that she's thinking it through as she's writing it. I think that's great.
If you recall, the change in potential energy is equal to, and I'm sorry that thing's on the way, is equal to the charge times the change in potential.
Yeah, I love this. This is so cool.
Is positive right here. We just talked about that. And that's an electron moving, so that's a negative charge. So positive times a negative will make this a negative.
Yeah, very cool.
Right. So now, if the potential energy
Ooh, that was cool how she got rid of this here.
Kinetic energy is going to go up. It's going to increase. So the change in kinetic energy is positive. So the only way that we can get the change in kinetic energy to be positive with speeds is if we
just trying to stay out of the way.
So I already have this circled. There we go. Yay! If you notice, we didn't actually calculate anything. How wonderful is that? Okay, so next slide. What direction is the force on the electron? So we have...
Okay, so I just want to go back a little bit. We'll stop it at this point in the video. Wow. I mean, these problems, you really need to drive it home. I thought you did a great job of really talking about the signs. My brain's sort of clicking away at ways you could extend this problem, but it's often too early to extend. I heard something really, really interesting. If you write a test question that you're super excited about, you should probably rethink it, right? So here's me thinking, ooh, it doesn't have to go directly from A to B, right? And ooh, the field could be some really, really weird thing. But no, her point in this problem is to help them navigate this terrible sign problem, right? Basically, this sign problem right here. That electrons screw everything up, right? If only we had named that to be the positive charge, so much less problems in physics. We could use our right hand instead of our left hand, all of that stuff. But I just think she did a really great job. First of all, of clearly thinking it through, of laying out the science, and I just loved this part because it's so hard if the students are taking notes and they're not really being careful with their letters. And as she said, there's a V for voltage and a V for for speed or velocity in this problem. So I thought this was really cool. All right, you guys, thanks so much. Have a great day, and remember, physics teachers are awesome.